let us see what is the best compression member among these hollow sections. So I told that three hollow sections are available: rectangular hollow section, square hollow section and circular hollow section. So now out of these three hollow sections, let us see what is the best compression member. As I told, have remember Euler's critical load carrying capacity of a compression member. When you calculate, we are having a formula pi square EI by LE square, and I told you that this PCR is equal to pi square E A by delta square, lambda square, sorry, slenderness ratio. If the slenderness ratio is minimum, then load carrying capacity is maximum. So to maintain the less slenderness ratio, we require higher radius of gyration. So essentially, the section which has higher radius of gyration will be the best compression member. I already explained that earlier. Just I explained I sections. I explained that concept. Just I am repeating that. So ideally, what I am trying to say here is that this particular PCR, load carrying capacity of compression member, as per Euler's formula, that is pi square EI by LE square. So essentially what happens is when I take when I put I is equal to AR square, so it becomes pi square E by LE by R whole square. So essentially my R minimum should be less. If it is less, if it is higher, this term will be less. If this term is less, then load carrying capacity is more. So this is what exactly you have to understand. Okay. Okay, so among all the hollow sections, which is going to give highest minimum radius of gyration, that is the best compression member. So among these three, rectangular, circular, square hollow sections, circular hollow section, very very important point is that circular hollow section has highest minimum radius of gyration. Highest minimum radius of gyration. Because it is having highest minimum radius of gyration, therefore it is the best compression member. It is the best compression member. It is the best compression member among all. It is the best compression member among all. So for a given cross section, out of all the possible sections of 10 types, not only among these three, circular hollow, hollow, square hollow, circular hollow, this one rectangular hollow, but among all the available sections of steel structures, circular hollow section is the best compression member among all the sections, among all the rolled steel sections. I can write best way, among the rolled steel sections. So please understand this. Among all the available rolled steel sections, circular hollow section is the only section which has the highest radius of gyration. If it has highest radius of gyration, lambda will be less. If the lambda is less, load carrying capacity is more. So that is what essentially you have to understand. So the very very commonly asked question in all the competitive examination, this question was appeared. Which of the following section is the most efficient compression member? That kind of question was appeared in the exam. The correct answer is that circular hollow section is the best compression member among all. It is also called as tubular section. So because this closed sections and especially circular hollow section, essentially we can also call it as tubular section basically. Okay, please understand it. And hollow sections are also called as box type sections. So please understand this point also. Hollow sections are also called as box type sections. Hollow sections are also called as box type sections or tubular sections basically. Okay. So this is also a question asked in the exam. Which of the following sections or most efficient in resisting torsion? The correct answer will be hollow section, but in some of the exams they are given box type section. That is also the correct answer actually. Okay, I hope you understand this. Now, dear friends, once the hollow sections are done, now let's go for the another type of section called as flat section. Okay, so what is a flat section? Where we are going to use the flat section? Let us look at that. So Indian standard rolled steel flats. So flats, where we are going to use, what are the flat sections? How to designate the flat section? So let us look at that. So this is essentially called as flat section. This is the flat section we are having. It is having certain width and it is having certain thickness basically. So my dear friends, you try to understand. This flat is having a width maximum of 250 mm and thickness of the flat should be more than 5 mm. Thickness of the flat should be more than 5 mm. And I can say that maximum width of flat, so maximum width of the flat is restricted to 250 mm. So please remember this, understand this. The maximum width of the flat is restricted to 250 mm, 250 mm. Now, my dear friends, you try to understand where we are going to use this kind of flat sections. So essentially, the flat sections we are going to use in the case of built-up columns. As I told, built-up column means if single column is not able to carry the load, two columns we place nearby and we connect them with the help of either lacing or batten system. Such kind of columns we use battening. For battens we are going to use the flat sections. Right. Not only that, if you want to make certain joints in steel connections somewhere, okay, we can go for the flat sections. And that is the main advantage of using flat sections. Okay. So how to designate flat sections? So flats are designated as, otherwise flat is designated as something like this, 100 ISF 10. What does it mean, 100 ISF 10? What does it implies? It implies that the number before ISF is indicating that width of the flat. The number after ISF is indicating that thickness of the flat. This is the thickness of the flat. Okay, I hope you understand this. Now we have something called strip. What is a strip? Let us understand that. Strip, S-T-R-I-P, strip. So strip is having a thickness less than 5 mm. This is the strip we are having. This is the strip. If the thickness is less than 5 mm, then it is called as a strip. If thickness is less than 5 mm, then it is called as a strip. So where we are going to use strips? Strips essentially, the basic difference between strip and flat is flat thickness is more than 5 mm, strip thickness is less than 5 mm. The strips where we are going to use, this strip we are going to use only to join the two plates. So whenever you want to join two plates, you essentially require this strip. So strip is required whenever you want to join two plates. So to join two plates, we need to have this. To join plates, strips are provided. Strips are provided. So strips are provided to join the two plates. Please remember this. And how to designate this strip? Indian standard ISST. We have certain width. The maximum width of the strip is limited to 1000 mm. So please understand, maximum width of the strip is restricted to 250. This is what B max, maximum width of the strip B max is equal to 1000 mm. So ISST, we have to first indicate the width of the strip followed by the thickness of the strip. Let's say it is 3 mm. That's all, nothing more than that. Okay, I hope you understand what is the difference between flat and strip. Okay, next. We have something called as plates. Oh, okay. So what are the plates and where we are going to use the plates? Let us look at that also. Plates are very important things. Generally, we use the plates as slabs. Plates are used as the slabs in case of pure steel buildings. We are going to provide that as slab. So these are used as plates are used as slab elements. Plates are used as the slab elements in steel structures, in steel buildings essentially. In steel buildings. Okay, please try to understand it. Now, when I talk about plates, plates are having certain width, certain length and certain thickness. So basically they are having something like this. So we have length, certain width and certain thickness. Length, width, and apart from length and width it has thickness, certain thickness also it has. Let's look at that. They are also having certain thickness. So length, width and thickness. So essentially when I say slab in case of steel buildings, we have to go for the plate itself as the slab. Look at any manufacturing of vehicles also. Plates, we need to have any truck, any bus, any train, whatever it is made of steel. We need to use slab, nothing but plate itself as a slab element. Okay, that's a very important one. And to call any a member as a plate, the thickness should be more than 5 mm. Then only we call it as a plate. And plate has substantially good amount of length and width. Okay, please understand that also. And we have something called strip. What is a strip? Let us look at that. Plates, sheets. We're talking about sheets. So the basic difference between plates and sheet is that sheets are used essentially thickness. If the thickness is less than 5 mm, if thickness is less than 5 mm, then we call the material as a sheet. Where we are going to use sheets, as a roof covering material. So it is used as roof covering material. It is used as a roof covering material in trusses, in roof truss buildings. It is used as a roof covering material in roof trusses of industrial structures. We use it as a roof covering material. Sheet is used as a roof covering material. I hope you understand. And how to designate that? Very simple. ISST. How do you represent plates? ISPL, Indian Standard Plates, having length of let's say 2000 and width of let's say 1500 and thickness of let's say 8 mm. It is said to be plate. And if you want to have sheets, Indian Standard rolled steel sheets, having width of 2000, let's say length, width of 1500, thickness is 3 mm, because I told as already, to call a material as a sheet, essentially its thickness should be less than 5 mm. Then only we call it as the sheet, otherwise we don't call it as a sheet. Okay, I hope you understand this. This is all about sheets. Now let us move on to what we call last one, what we call bars, Indian Standard rolled steel bars. So what about bars? When we can say them as bars. So bars are of two types actually. One is the round bars, the other one is the square bars. These are the two things we are having. One is the round bars, the other one is the square bars. So how the round bars, round bars are to be something like this. Essentially they are having certain radius, certain diameter. So, and we have square bars also as well. That's like this, something like this. This is what it is, square bar. This is the round bar. So we represent with ISRO, Indian Standard round bars, let's say 50. So what is the meaning of that? Indian Standard round bar having diameter. This is what it is, diameter. Diameter of the round bar is 50. And Indian Standard square bars, we can say ISSQ, let's say 50. Nothing but dimensions. Square, no, it's both dimensions are same. Square means essentially. So this is how these bars are actually. So now where we are going to use these bars. So bars are essentially used as a light compression members. So these are used as light compression members. So these are used as light compression members. These are used as light compression members. So please try to understand this. So whenever there is a light compression members are existing, we can go for the bars. So these are all the different types of rows, the sections we are having, and the corresponding utility where we can use them. That is all about this kind of things. Now once all these roles and sections are done, now let us focus on to what are the material characteristics. So when I take a steel, what are the properties of the steel, where it is strong, where it is weak, where it is moderate, and what are the stresses correspondingly we should take, and what are the methods available for design of steel structures. So we'll be talking about all these things, okay, one after the other. So before going into the methods of design of steel structures, let me talk about what is the typical behavior of steel, basically how it is going to behave. Let us look at that. So when I talk about these steel, actually what happens is that this steel is basically, everybody knows that it's a ductile material. What is the advantage of ductile materials? So I can say main features or main characteristics of brittle material. So ductile material, when I talk about steel, so steel is basically ductile material. Steel is a ductile material, and if it is a ductile material, what are the basic properties? Let us look at those basic properties now. So when I say ductile material, steel is one of that category essentially. And what are the basic properties of steel? You know, when I talk about steel, steel is very strong in one particular area, and steel is moderate in particular area as well, and steel is very weak in some particular areas, right? So essentially we have to understand where it is strong. Very strong in case of tension. So steel is basically very strong in tension and moderate in compression. Steel is moderate in compression and very weak in shear. Actually steel is very weak in shear. So please understand, these are the very essential thing which you have to understand throughout steel structures. These are the basic property of steel material or any ductile material. Basically they are very strong in tension. Steel is very strong in tension, moderate in compression and weak in shear. The biggest drawback for steel is shear is the drawback. Most of the time when you apply force on steel material or metal, it is going to fail by shear. So please try to understand that, okay. So what happens is that shear failure, when you apply tension, basically what would happen? So you might have heard about, you know, testing of steel bar, mild steel bar under tension. Let's say this is what it is. Testing of mild steel bar under tension. If you do it, what happens? So when I test this mild steel bars related to tension, actually what is happening, you try to understand that when you apply this kind of tensile force, because of this tensile force, there are, even though the applied force is tension, there are some kind of Ludar cracks we are going to get, and those are almost 45-degree cracks, and this is going to fail by giving crack. That is what we call shear crack. So shear cup cone failure we can find. If not this exactly, we can say Ludar cracks. We cannot even notice them, these kind of things at the point of cup cone failure. But actual cup cone failure would look in this fashion. So when you apply tension on this steel bar, we can have this kind of effect. We can have this kind of cup cone failure. Essentially, we can have this kind of failure. This kind of failure we can have in the steel actually. So this is the cup cone failure. Okay, which is basically the shear failure, even though the applied force is tensile force, but it failed by shear. So that is what you have to understand. Okay, so steel is very weak in shear, so shear failure is most dangerous failures for steel. So our Indian standard is saying that IS 800 2007 is saying that, so whenever there is a shear, you have to be very, very careful. Whenever there is a shear, you apply the additional factor of safety as root 3. That is additional factor of safety which we have to always use. Let me explain about that clearly. So because steel is very strong in tension, a material which is very strong in particular area, in that case we can go for the full capacity. We can make use of its full capacity. So we have two kind of stresses we have. One is there are two stresses we have for material. So stresses or strengths. There are two strengths we are having. One is the yield strength Fy, and another one is the ultimate strength. These are the two strengths we are having. So whenever there is a criteria of strongness, ultimately we know that ultimate strength is the maximum strength it can bear, and yield strength is this is the moderate, we can say. Material does not fail generally at yielding, almost it is like elastic behavior. So that's why in design we go for the yield stress most of the circumstances. In exceptional case we can go for the ultimate stress as well. You have the right to use ultimate stress only only in a case where it is very strong. So steel where it is very strong, steel it is very strong in tension. So whenever there is a tension, you are going to use the ultimate stress. The rest of the cases we are going to use only yield stress. And one more thing, whenever there is a criteria called rupture fracture, essentially rupture or fracture occurs essentially when there is a what we call ultimate stress is reached. So when the ultimate stress reached, then only we can have this kind of rupture or fracture. So these are the things we have to understand. So these are the strongness and weakness. Now we'll see what are the working stress that is permitted at different circumstances. Let us look at that. So we can say what we call nature and the corresponding working stress. So what is the nature of stress applied and the corresponding working stresses? What are the corresponding working stress? Let us look at that. So nature, first we talk about tension. So when I talk about tension, essentially tension, which is the working stress which we can take for tension is ultimate stress. And when I talk about compression, so when I talk about compression, the stress that I am going to take is yield stress. The moment I talk about bending, when I talk about bending, what is the stress I should take? That is what you have to think and tell. So when there is a bending, essentially, bending, you take, a good example is beam. When there is a beam and you apply a load, it is going to bend, right? Okay, yes, because supports are there at the ends, there is no support at intermediate location. When you apply a load, it is going to bend in the middle region, okay, basically away from the support there is a bending. Bending moment is 0 at the support, because at support it is not offering the member to bend actually. So if that is the case, and we found that bending has two things, bending compression as well as bending tension. So now the thing comes which is weak for steel, is bending compression is weak or bending tension is weak? That is another question mark we can have. So this one we can address basically when there is a bending compression, basically when there is a bending compression, When compared to bending tension, bending compression is the critical thing. So when I talk about a steel, that's what I said, steel is moderate in compression basically. And very strong in tension, that's not a problem, but moderate in compression. Because it's moderate in compression, so we can use that weakest part. That the weakest part is compression when compared to tension, therefore we can use moderate stress. So I can use only yield stress even in beam design. So when I say beams, throughout beam chapter, design of beam, steel beams, what is the stress I can permit is yield stress only. So when there is a compression throughout compression members chapter, the stress that I can permit is only yield stress. When I say tension, the stress that I can permit on steel is ultimate stress. I hope you understand this. Okay, that's all. And very important thing is that when I talk about fracture or rupture, so please make a note of this. If you understand this, you literally play with steel structures. Rupture, fracture, this kind of terms if you find, then the stress that we can admit is only ultimate stress. So please make a note of this, very, very important. I can say very, very important. If you really understand these four things, what stress to be taken at what circumstance, if you know really, you are going to write the formula on your own. Any kind of formula you can write on your own if you really understand this. So in steel structures, when I say tension, the stress that you are going to take is the ultimate stress. Then steel structures, when I say compression, the stress you are going to take is yield stress. The moment when I say bending, the corresponding stress what you are going to take is the yield stress. The moment when I say fracture or rupture or tearing, even tearing also, when I use the term tearing, rupture, fracture, these three kind of terms, if you come across in steel structures, the corresponding stress we are going to take is the ultimate stress. Now come to the point, dear student friends. As I told not I told, but material behavior is telling us that the steel material is weak in shear. Because it is weak in shear, our code says that you accommodate the additional factor of safety. Our code is saying very clearly that in case of steel in shear, there should be additional factor of safety that we have to apply in order to compensate its weakness. Okay. So I hope you understand. Whenever there is a shear, in case of steel, it is weak in shear, then we have to apply the additional factor of safety for the steel if it is a shear comes into picture. I hope you understand this. Now once you understand, these are the working stresses, and now let us focus on to the philosophy of our steel structures design. So we'll see one by one, then accordingly we are going to apply the corresponding factor of safety. What is the factor of safety? What value we are supposed to take in what circumstances? So we see those things very, very clearly one after the other. So now let us move on to the what is the philosophy of limit state design? Okay, what are the methods of design of steel structures? Let me talk about that. That is not much important, but only important for is limit state design. So let us talk about only methods of design of steel structures. Methods of design of steel structures. So what are the methods available for design of steel structures? There are basically three methods available for steel structures design. One is working stress method. It's very important. Earlier we used this method, working stress method. And the second one is ultimate load method. We are using something called as ultimate load method. And the third one is what we call as limit state design. Limit state method. So these are the three methods available for design of steel structures. So, but out of this, the second one nowhere we are going to use. Practically, we never ever use ultimate load method. It's only theoretical concept. Working stress method earlier we used to use as per the provisions of IS 1984. We have working stress method. Okay, let me write corresponding codes also here. Working stress method is corresponding to IS 800 1984, and we are using latest code IS 800-2007. This is the latest method of design of steel structure, and however we are not going to use ultimate load method. Okay, so working stress method is basically, when I look at working stress method philosophy, the philosophy of working stress method is that the material strength need to be underestimated. That is the only philosophy of working stress method. Always working stress method is saying that whenever you want to design steel structures or reinforced cement concrete structures for that matter, whenever you want to design any kind of structures, essentially what you have to look at is that the material should be at low stress condition than its maximum capacity. Whatever the capacity of the material is there, you try to apply a stress, apply a load or whatever it is, loads, which causes or which induces a stress less than their permissible stress. And then we can say that the material is safe. Okay, that's what the very simple philosophy of working stress method is, that underestimation of material strength to the maximum possible extent, to the maximum safest possible extent. That's why in working stress method, factor of safety is used are very, very high. Okay, that is the biggest drawback we are having. That's why when you use more factor of safety for material stress to keep the material to be at low stress condition, what happens is, if the material is at low stress condition, essentially what happens is that the area required for resisting a particular load increases. The area required to resist a particular load increases. When the area is more, dimensions are more. When the dimensions are more, we can say that investment is more. When the investment is more, we are not going to, people not in a position to accept that. Okay, that is the biggest problem we are having. That's why working stress method is having only drawback is that it's uneconomical method. But safety wise it's well and good, because as long as you are in low stress condition, the material is safe. Please understand that. That is the only format we used in working stress method. What is the only format is? It is only the what we call basically safety format. Only material stress should be underestimated. Remaining all are automatically taken care. Okay, that is what working stress method is. That's why only drawback of working stress method, as I told just now, it is uneconomical. Because of what is the only reason? Uneconomical because of higher factor of safety for material. Because of higher factor of safety of material. Because you considered higher factor of safety of material, that's why it is giving uneconomical sections, more dimensions. Now we have next one, limit state method. What does limit state method is saying? So limit state method, what does the limit state method is saying? So limit state method philosophy is something different. Okay, before going to limit state, we have something I written here, because I written there, I have to say that ultimate load method is not at all safe concept. The reason is that no factor of safety is applied for material stress. Please understand that material stress, there is no factor of safety. That means the material to be stressed to its full capacity. So understand, dear friends, any material, if it is subjected to maximum stress or ultimate stress every time, there is a possibility of failure of the structure takes place. So that's why there is no safety at all when you go for the ultimate load method. That's why it is no longer existing practically, it is only a theoretical concept. Now coming to limit state method, this is what is our concern is now. This is very, very important for us. So this is the latest method available at present for the design of steel structures in India. Okay, and we follow strictly the recommendations of IS 800-2007. Now my friends, limit state method. If I take a limit state method, limit state philosophy, if you look at, it's quite interesting when compared to working stress method. This philosophy is something quite interesting. Let us look at that. What is the philosophy of limit state method? The philosophy of limit state method is that overestimation of loads acting. The first thing is that, the first thing you have to understand that overestimation of loads. How do you do that? So, overestimation of loads acting on structures. Overestimation of loads acting on structures. So, what does it mean? What is the meaning of overestimation of loads acting on structures? So, when I say overestimation of loads acting on structures, what does it mean? That means at present some load is acting on structure, but we don't care for the present load. We are going to take care of the future load. Listen, at present some load actually existing on a structure, it is not guaranteed that the same load will be there in future after 15 years, 20 years, etc. So, that's why there is an uncertainty of loads which may be existing in future. To take care of those uncertainties or untold circumstance based loads, there is a load factor of safety we have to consider. That's what we can say, that overestimation of loads. That means the structure should be designed for higher loads. Okay. So, what is the intention of this one? The structure should be designed for the structure should be designed for what? Extra loads, excess loads. The structure should be designed for excess load or extra load. Please understand it. That's why excess load or extra load than present load. Okay. That's why the thing comes called as design load. So, what is the design load? When I say design load, gamma F times working load. This is what the philosophy we are following. Design load is equal to gamma F times the working load. What is gamma F? Where gamma F is the partial safety factor for loads. Where gamma F is equal to partial safety factor for loads. Partial safety factor for loads is gamma F. This partial safety factor for loads, gamma F, is dependent of load combinations. What kind of loads we take? So, we have separate code for loads acting on structures. IS 875, we have parts in it, part 1, part 2, part 3, part 4, part 5. We have dead load, live load, wind load, snow loads, accidental loads, etc. Okay. And earthquake load, we have IS 1893, separate code is there. Okay. So, now my dear friends, please understand that depends upon the load combinations, this gamma F value is going to vary. And if it is generalized thing, gamma F is taken as 1.5, generalized case. Okay. If nothing is given, just you multiply this working load with the 1.5, you get the design load. So, all these things will be discussed in case of reinforced cement concrete. The same thing will be followed here. Okay. Now, let us understand, this is not only the philosophy, this is only first philosophy. There are two things are there in limit state philosophy. One is A, that is overestimation of loads acting on structure. That means the structure should be designed for the excess loads than the present condition. Why we are designing the structure for excess load? Because in future the probability of increase of loads on structure may be possible. To take care of that uncertain future loads, we are taking the gamma F. That's what it is. Now, we have something what exactly we call as underestimation of material strength. That is another philosophy of limit state method, that is underestimation of material strength. Underestimation of material strength. Underestimation of material strength. So, how do you underestimate material? What is the need of underestimation of material strength? So, material strength always need to be underestimated. Why it is so? The reason behind why we have to underestimate material strength is that very simple. Whenever you take a material, it has some specific or limited capacity. Every material for that matter, any kind of material you take it, it has certain limited strength. Okay, and that limited strength is basically what we call as In case of working stress method, permissible stress. Here in limit state method, we call it as design stress. Design stress is the maximum stress we allow, including some factor of safety. So, what our code is saying is that whenever you apply some stress on a material, that stress should be in such a way that it should not reach the full capacity. Whatever the stress capacity is there, full stress capacity, that much stress it should not undergo. If it undergoes that much stress, it fails. So listen, our code limit state based approach is saying that know where our material should fail. That is a major concern. None of the cases our material should fail. That is what, none of the cases. That's what it is, intention of code. So material strength need to be underestimated. That's why there is a term called as design stress. There is a term called as design stress. How would you get design stress? Very simple. When I want to get design stress, very simple thing is that working stress by factor of safety. So the working stress by factor of safety will give you the design stress. So design stress is equal to working stress by factor of safety. So what is the working stress? Actual stress. The term, when I use the term working in civil engineering, irrespective of the subject, whenever I talk about something called working term, working means actual or original. So actual stress carrying capacity is something, but we never allow the material to take its actual capacity, because if it reaches actual capacity, it fails. Original capacity or actual capacity. That's why we always, the original stress should be divided with the factor of safety. For that stress, we take it as the upper limit, and we always ensure that the stress developed on the material should be within the design stress. Okay, that is how we are going to design any kind of structures, not only steel structures but even RCC structures as well. Then material factor of safety depends upon the what kind of stress we are taking and what kind of fastener you are designing and what kind of failure condition you are considering. According to that, we are going to take the design stresses. I hope you understand that. Now, my dear friends, when I talk about, so I already know working stresses. Some of the cases I already given working stresses. You know working stress, if you want to look back, I already given those things here. So what is the nature of stress and what are the corresponding working stress? If it is tension, the corresponding working stress is ultimate stress. Excuse me. If it is a compression, the corresponding working stress is Fy. If it is a bending, the corresponding stress is yield stress. And if it is a fracture or rupture or tearing, the corresponding stress is ultimate stress. So you know all the stresses, working stresses, but I want design stress. So when I talk about design stress, the working stress I need to divide with the corresponding factor of safety. So look at here, my dear friends. I have working stress. The working stress need to be divided with factor of safety to get the design stress. That is what we have to understand. Now, dear friends, I want to know what is the design stress in compression. How would I get design stress in compression? Let us look at that. So design stress in compression, if I want to find, how would I get? Very simple. So design stress. So design stress in compression. So what is the design stress in compression? The design stress in compression, if you want to get, what is the working stress in compression? Yield stress. What is the corresponding factor of safety? Gamma m naught. So please understand, whenever there is a yield stress, the corresponding factor of safety is gamma m naught. So I am going to represent here gamma m naught means factor of safety against yield stress. Factor of safety against yield stress is gamma m naught. Gamma m1, which is equal to factor of safety against ultimate stress. Factor of safety against ultimate stress is gamma m1. Okay. So the gamma m naught value is taken as 1.1 every time, and gamma m1 is 1.25. Please understand this. Okay, these are the yield stress factor of safety. This is the ultimate stress factor of safety. Okay, What is the design tensile stress? Let us look at that. Design tensile stress. How to get design tensile stress? When I say design tensile stress, in tension the stress per unit is ultimate stress and the corresponding factor of safety is gamma m1. Okay. Now we have what we call shear also. My dear friends, let me tell you here, when there is a shear, shear may be caused by two things. When you apply tension, shear comes. When you apply compression also, shear is going to comes into picture. So, according to the nature of shear, sometimes shear may be occurring in yielding, sometimes shear may be occurring in tension also. That is, two things are there. If the shear is occurring due to compression or yielding shear, then we are going to take yield stress only. If there is a shearing occurring because of rupture, then we take the ultimate stress. Okay, please try to understand that. Okay, design compressive stress is Fy by gamma m naught. Gamma m naught value is factor of safety against yield stress, which is 1.1. And design tensile stress, if I want to take it, is Fu by gamma m1, where gamma m1 is 1.25. Now, my dear friends, please understand that when I talk about design shear stress, in yielding, let's say, design shear stress under yielding is the criteria for shearing. If shear yielding is happening, then I can say that yield by corresponding factor of safety gamma m naught. My dear friends, I told you already that you try to understand that steel is weak in shear. Because steel is weak in shear, we will be using additional factor of safety. The additional factor of safety for shear is root 3. But the additional factor of safety for shear, root 3 is the additional factor of safety recommended by Indian standard. So, if you want, I will write there itself so that you will not get confused. So, because steel is very weak in shear, part, so we need to have additional factor of safety which is equal to root 3. So, root 3 is the additional factor of safety recommended by our Indian standard. Okay, please try to understand this. Okay, so what is the design shear stress in yielding? It is Fy by root 3 gamma m naught. What is the design shear stress? What is the design shear stress in rupture or fracture? Design shear stress in rupture or fracture. So, when there is a rupture or fracture or tearing, I use these terms, under these cases shear occurs, for example. Design shear stress under rupture or fracture or tearing, as I told you, when I talk about rupture or fracture or tearing, ultimate stress will come. The corresponding factor of safety is gamma m1, and because it is happening in shear, there is a additional factor of safety root 3. Okay, please understand, when I talk about a shear, always additional factor of safety comes into picture. So, please keep this into mind. So, when I say shear, root 3 comes automatically. Whenever there is a shear, root 3 comes additionally. Please understand that. Okay, these are the very important things which you have to understand. When I say bending stress, design bending stress, how do you take? I told that even in bending also two things will happen. One is the bending compression, the other one is the bending tension. So, I hope you understand that. So, any one of these may be taking place. Design, okay, so accordingly we should take, okay, fine. But out of this bending, compression and tension, what is the critical one? Compression is critical, though therefore Fy by gamma m naught. So, in case of beam, if there is a shear occurs, then you can take yielding based one. So, Fy by root 3 gamma m naught. So, please understand that. If you understand this, these are very, very simple things, don't think too much. So, very, very simple concepts. Once you understand this, you can write any formula in steel structures. Okay, I hope you understand. So, beam also the stress allowed is the yield stress, because beam is a compression, bending compression member, only yield stress. Compression whatever you are taking, the same thing will come for B1 beam also. I hope you understand this. Next, once you know how to find, these are all the design stresses. When there is a factor of safety in denominator, all these things are the design stresses. All these stresses are the design stresses. I hope it is clear to every one of you. Fine. So, after this, what we supposed to do? So, once all these things are done, we have to see that what are the limit states we are having, how many limit states we are having, and what are the checks that are permitted under this case, we have to check. Okay, fine. Now, let us see that part now. Limit states, how many limit states we are having. So, what is mean by limit state or limiting state? The name itself it is telling us limit means maximum possible. So, limit state is telling us that at what maximum condition the material is going to fail, that is what we actually call as limit state. It is the maximum most possible case where the material is about to fail, that is the limit state. Okay, fine, but we try to ensure that the structure should not reach to limit state during its intended lifespan. That is what our concern is. So, okay, then if you are very much sure that it should not reach the maximum stress during its survival life, what are the safety measures we should take when we design? So, there are two aspects of limit state method. One is the limit state of collapse, or people also call limit state of strength as well, and limit state of serviceability. Okay, there are two limit states we are having. One is the limit state of collapse. Let me talk about that. Limit state of collapse. This is the limit state of collapse. And we have something called limit state of serviceability also. We are having limit state of serviceability. Two things are there, limit state of collapse and limit state of serviceability. So, limit state of collapse is also called as limit state of strength. Limit state of collapse is also called as the limit state of strength, and limit state of serviceability, anyhow you know this. Okay. Okay. That means that any structure we design, it should be safe against limit state of collapse aspect and limit state of serviceability aspect. Means, try to understand, dear friends, whenever you design any structure, one important thing is it should not fail or collapse at any state of intended its intended lifespan, right? We know that. That's why there are some failure criteria we are having, some failure criteria, collapse or strength criteria. Let us look at them. And once the strength criteria are satisfied, then only we have to go for the serviceability checks. As long as it is not satisfying strength aspects, you should run here only. You should do iterations and ensure that it should be safe in strength. Then only we can go for the serviceability aspects. Okay. What comes under limit state of collapse? We can say limit state of collapse against limit state of collapse. Limit state of strength or collapse against limit state of strength or collapse against limit state of strength against yielding, limit state of strength against yielding, buckling. Then we have something called flexure, shear, and limit state of strength against plastic collapse. There should not be any plastic collapse should takes place. Then we have even brittle fracture. So, the material should not fail by brittle fracture. And we have and stability aspect, whatever stability, safety against stability, like overturning, etc. You can say stability against overturning, sliding, etc. So these are the major limit state of strength aspects. Limit state of strength against yielding, buckling, flexor, shear. Limit state of strength against plastic collapse. Limit state of strength against brittle fracture. Limit state of stability against overturning, sliding, etc. Okay, these are all the strength aspects. Now, if you talk about limit state of serviceability, so we have deflections. It should not fail by deflections, and we have it should not fail by fire attack, and it should not fail by corrosion, and it should not fail by excess vibrations. So these are all comes under limit state of serviceability. So what does it mean actually? It means that the structure whatever we design, whatever so you design, it should not fail by strength aspects, it should not fail by serviceability aspects. Okay. So we have every aspect, whatever the member you are going to design, we have certain guidelines, how to design for flexor, how to design for shear, how to ensure these failures will not happen. There are proper checks given by Indian standard, and those serviceability aspects are checked once it is passing the strength aspect. I hope you understand this. So this is all about the limit state. Why we are doing in limit state factor of safety for loads as well as material strength? Okay, that's why the name came partial safety factor for loads. Why partial term comes into picture in limit state design? Because the reason is some factor of safety is allocated to the loads and some factor of safety is allocated to the what we call material strength. That's why it is a partial safety factor term we are using in case of what we call limit state method. I hope you understand this. Okay. Next. So once it is done, a limit state is satisfied, then we can say that whatever the structure we designed as per the IS 82007 limit state method is safe in all aspects. Okay. So that is all about the very basic fundamentals of materials and specifications in the steel structures basically. So all these things you must remember. Whatever I started from the beginning, how steel, what is the hot roll sections, and what is the steel, how carbon content influences. So then after that we moved on to what are the different types of hot roll sections we are having, what are the practical applications, what are the difficulties we are having, right? And how the philosophy is framed, what is the philosophy for working stress method, what is the philosophy for ultimate load method, what is the philosophy for limit state method. So all these things are being discussed. So please remember, uncertainties are the biggest challenges. So material uncertainties, in load estimation also uncertainties may be happening. Okay, many things are there. So all these uncertainties, whatever made by human beings, that will be taken care by the factor of safety. So factor of safety plays a vital role in the design of any structure you take it. Any structure, it may be RCC structure, it may be steel structure, doesn't matter. Always remember that there will be some uncertainties may be existing. So all uncertainties are taken care by the factor of safety itself.